Hello everyone, and in order to prepare ourselves for my upcoming round 3 fight with environmental science, let us fortify our minds with some integration today. So here we have this fun little integral I found off the Stack Exchange. So let's go get cracking, shall we? The first thing we're going to do is just do a quick little u sub. So we're just going to let u equal x squared. That way we'll be able to do some complex analysis with this. And we're also going to change our bounds. So change bounds. And just notice that this integral right here is actually symmetric. So we're just going to say it's 2 times the integral from 0 to infinity. And then apply our u sub, which means that we're going to have our integral from 0 to infinity still. That part's not going to change. But what will change is this e term, this e to the minus u, and then times this cosine of a and then u. And then 1 over the square root of u, where the extra factor of 2 is canceled out by the fact that this integral is indeed symmetric. So that right there is equivalent to our original integral. But what's interesting is that cosine can actually be expressed in terms of e. We can just say now that this is equal to the real part of the following integral using Euler's identity. So 0 to infinity still, of course. We have e to the minus u and then times e to the a I u. And then square root of u du. But we can simplify this even further, just grouping our terms inside of that exponent. What we find is that this is just the real part again of the integral 0 to infinity. Again, that part's really not changing. And then just 1 minus ai. And then times u over the square root of u. And then du. Now, how exactly are we going to evaluate this integral? Well, to do that, what we're going to do is actually take a detour. A detour, you might ask, but you never digress. I'm kidding. I obviously do digress. Much more than I let on, because there's a handy trick called editing. But anyways, consider this function right here. So just consider f equaling e to the minus u, and then just divided by the square root of u. And then also consider the following contour. So if those were our axes in the complex plane, consider this contour right here, where we're integrating around this pizza disk. Or actually more precisely, we're integrating around the origin with our pizza. So we take a pizza and then we have a pizza, then we take a little bite out of the pizza. So by the residue theorem, what is this going to equal? Well, there are obviously no residues enclosed by this contour right here. We might have some interesting behavior at 0 because we have this 1 over square root of u. Spoiler, we don't, but anyways, this whole line integral is just going to equal 0 as there are no residues inside. We also know that we can split up this contour integral into individual integrals. So call this the integral over gamma 1, and then gamma 2, gamma 3, and then gamma 4. So let's just go ahead and evaluate each one of these separately, shall we? So gamma 1, gamma 2, plus gamma 3, and then plus gamma 4. All right, let's go ahead and evaluate gamma 1. So number 1, the way we're going to evaluate this right here, or show how it goes to 0, is just by saying, well, u is just going to equal some r e to the theta I, right? And we're just going to take the limit as r goes to 0. And substituting this in, we see, well, we're integrating the bounds here don't necessarily matter, but what does is the fact that we have this e to the minus r e to the theta I, and then we have times 1 minus ai. Then we have r times e to the theta I, and then divided by the square root of r times e to the theta I. So we're just going to have all this inside of a square root, and then d theta right there, and we're going to have an extra factor of I out front. But as said before, this right here is just going to go to 0, because if we have, say, the square root of r times e to the minus r, and take the limit as r goes to 0, it's pretty simple to show that that right there is just in fact 0. So this right here ends up approaching 0 in the limit. Now let's go on to the other one that is just going to be 0, and that's going to be the other odd one, number 3. Where we're going to take this, but then just take the limit as it goes to positive infinity, right? And it's pretty easy to see that that right there does just go to 0, because we have this e term right here, And even though the square root of e to the theta I is growing, this e term is eventually just going to win out. So this right here is also going to approach 0. Going on to things that aren't 0, we have the integral over gamma 2. So the integral over gamma 2. And this right here is just going to be the integral over all real numbers of this function right here of Rf. But we know that the integral from 0 to infinity of e to the minus u over the square root of u du, well, that right there is just going to be gamma of a half. And we know that gamma of a half is just the square root of pi. So that's plain and simple. What about gamma 4? What exactly is gamma 4? Well, that depends how we're going to define our contour, actually. And because we want to be finding this integral right here, we can define it as such. We can say that we're integrating from infinity to 0, because you can see the direction right there. And what we're going to do, our transformation to obtain this, is going to be u is going to just be 1 minus ai, and then times some t. And what we get is, I'll do the dt first, so we have 1 minus ai, 1 minus, or ia, it doesn't really matter the order, and then times e to the minus 1 minus ai t dt, and then divided by the square root of 1 minus ai, and then the square root of t. I'm just separating those terms out real fast. And what exactly does this equal right here? Well, factoring out all of our 1 minus ai's, what we find is that this is equal to minus square root of 1 minus ai, and then just times our original integral, where the minus sign comes from just changing the bounds. What we have then is our two integrals right here, which we know equal 0. So one is just the negative of the other, right? So we know then that, scrolling over here, 1 minus ai times I, well, the 1 minus ai is in the square root, but you can see that. All that is equal to just the square root of pi. So how exactly do we take care of this? Well, we can just solve for I real fast, right? So I equals the square root of pi, and then times 1 over the square root of 1 minus ai. But what exactly is this right here? Because remember, we needed to take the real part of all this. So really, you need to take the real part of both sides. So what is the real part of 1 over the square root of 1 minus ai? So to evaluate this, let's rely on the complex exponential and consider what 1 minus ai is equal to in terms of that. So the magnitude of this is just going to be the square root of 1 plus a squared. We just get that from squaring the real parts and the imaginary parts, or in other words, multiplying it by its complex conjugate and then just taking the square root. Then we're going to have our e, and then I times the argument of 1 minus ai right here. But what exactly is the argument, or really the angle, this point makes with with the real axis in the complex plane? Well, we can just find that by using arctangent. So visualizing this, we have, so this is our complex plane, right? We're going to be over 1 right here, so that's 1, and then we're going to be down some minus ai down here. So the angle of that this makes with the real axis, we can just find with arctan. So this right here is going to be the square root of 1 plus a squared. And then we're going to have e to the I, and then times arctan of just minus a over 1. But note here that this is 1 minus ai, and in our integral right here, we have a 1 over the square root of it. So we just need to raise this to the negative 1/2 power. So what this becomes is just going to be, well, 1 over 1 plus a squared, 1 plus a squared to the 1/4, and then times e to the minus 1/2 I, but the minus signs will cancel. So you just have I, and then over 2 times arctan of a. But note here that we can just take the real part of this directly now, because there are no fractions involved. We just have an e to the I something. So this right here, it's just going to be cosine, because again, it's the real part. This right here is just going to be cosine. So cosine of 1/2, and then arctan of A. And now this is just a simple question of what on earth is cosine of 1/2 arctan of A? And the answer to that, we won't be proving it in this video, but we're just going to rely on some handy dandy half angle formulae, or just a formula, half angle formula. And that is that the cosine of some theta over 2 is actually equal to the square root of 1 plus cosine of theta, and then divided by 2. I suspect that if you wanted to prove this, you'd probably just start by squaring both sides, and then do some stuff with cosine squared and some of the squared formula. But anyways, cosine of 1/2 arctan, well, using this right here, this is just going to be equal to cosine, or sorry, square root of 1 plus cosine of arctangent, which we know is just 1 over the square root of a squared plus 1, and then just over 2. We know that cosine of arctangent, I'll write this out, so cos of arctan right here is equal to that. Because this right here is equal to 1 over secant of arctan of A, and that right there is just equal to 1 over the square root of tan squared arctan, so A squared, and then just plus 1. So just a couple trig identities there to get to that. But the main event right here is, in fact, this. So what we have is we've evaluated this part right here, so let's go ahead and plug that into our main formula above. So bringing this over down here, we see that we have, well, the square root of pi, and then over 1 plus a squared to the 1/4, and then times our results that we just got. So that is just going to be the square root of 1 plus 1 over the square root of 1 plus a squared over 2. Close those parentheses, but we can actually simplify this a little bit. If we multiply the top and bottom by 1 plus a squared to the 1/4, we can simplify the outside to just the square root of pi over 1 plus a squared, and then on the inside we just have to multiply by the square root of 1 plus a squared. So we have big square root, and then the square root of 1 plus a squared, and then plus 1 divided by 2. And that right there is just, in fact, our answer. So there you go, kind of a shorter little integral today. And I hope you all enjoyed, and I will see you all in the next one. Thank you for watching.